Dr. Hainlein, we are so excited to hear from you today. I don't think you could have a more enthusiastic group, although this week maybe you have. But this is Dr. Kevin Hainlein. He is an astronomy professor and researcher on the James Webb Space Telescope science team at the University of Arizona's Steward Observatory. His research focuses on hunting for hidden supermassive black holes, and he's currently helping plan the initial deep observations to be done by James Webb Space Telescope to find and understand the most extreme distant galaxies in the early universe. He received his PhD from UCLA in 2012 and spent 3 years as a researcher and professor at Dartmouth College in New Hampshire, before moving to Tucson to work on the James Webb Space Telescope. Kevin has a passion for science outreach education and has spoken about astronomy and our relation to the stars at events around the world. And I cannot tell you how excited we are to hear from you. So welcome, Dr. Hainlein.
I appreciate that introduction. Welcome to the most surreal week of my life. This has been an incredible journey the last couple of days, and I'm really excited to share some of what we've been showing everyone this week and talking a little bit about that. I've spoken at this teacher symposium a couple of times before at the Biosphere, and I want to, because I know that we've got a lot of educators here, and I want to tell you how important it is for you to be doing what you're doing. I could not be where I am in my point in my career if it wasn't for the teachers that I had growing up in science. And I remember them by name. And I remember a couple years ago, maybe 5 to 10 years ago, running into my high school physics teacher, who really opened a lot of doors for me at a mall. And she was like, "Oh my gosh, Kevin, of course I remember you. I've been keeping track." And it really warmed my heart, because I was a tough, weird student who talked a lot, and I needed a special type of teacher, and I was really happy to find them at my public school. So I really appreciate the work you're doing, and I'm hoping that you continue to inspire future generations of scientists in the way that I've been inspired by my teachers. So we're going to talk today about this telescope here. If this is your first time, if you've been under a rock and you have never heard about this telescope, you're in for a real treat, because this is an opportunity for me to talk about the telescope in a way that I have not ever really been able to up till now, because I've been working here at the University of Arizona on the telescope for about 8 years, and I've given talk after talk after talk where at the very end I'm like, "And it's coming," and I've been showing simulated images and all these sorts of things, and then I would open it up for questions, and everyone would ask questions for hours and hours and hours. Say, they'd ask all these questions being like, "What if it breaks? What if it breaks? What if it breaks?" And I'm here to tell you right now that what's really incredible and why I'm excited to talk to you is that it did not break, and it works. And it's really the joy of my life to see how the world is responding to this. So we'll talk about it a little bit. So as was said, I'm a JWST NIRCam project scientist. NIRCam is the main camera on board JWST, and I work on that and have worked on that camera for years, helping as we've tested the instrument while it's been on the ground, before we even attached it to the telescope, making sure that it works the way that we thought it would while we have it here on the ground and could have fixed it. And then I tested it after we attached it to the mirror in Houston. We went out to Houston for a number of months. Even during Hurricane Harvey, I was actually in Houston during the hurricane, shuttling for 12-hour shifts and sleeping under the desks at NASA Johnson Space Flight Center so that we could test this instrument in cryo. And then I tested it in Los Angeles while we were putting the whole thing together at Northrop Grumman during a global pandemic. There's been a lot of stuff. The world has really given us a lot of challenges and delays as a result of those challenges. But it's been the joy of my life. I'm not the only person. I am here and excited to talk with you, but this could not have been done if it wasn't for hundreds of thousands of people. And I'm highlighting some of the people here who work on the team that I'm on, including on the far left, you can see Marsha Ricci. I don't know if you can see my mouse here when I do this. If not, I'll have to adjust and kind of just gesture with things. But on the far left, you see Marsha Ricci. She's the PI of NIRCam, the primary investigator of the instrument, and she's the one who hired pretty much everyone in this image here. But we're a team. This is a small number of the team. These are just people here, as seen in mission operations out in Baltimore, where we've been for the last 6 months, making sure the instruments works the way that it was designed to, making sure it met all of the requirements and hit the thresholds that we set out when we built the instrument. We were said, we will make it this sensitive, we'll make it this, have all these ability to resolve these sorts of things. And we've been doing that in mission operations. And you can see us all sit in front of computers or in front of the NASA logos. And I'm really happy to have worked with this team. It's been incredible. It's been incredible. And so I urge you, what's been also fun about this is that I've been able to see a lot of these people, their names in the news and recently, because we've all been interviewed by various folks. And it's fun that we're kind of spreading the love so that everyone gets a chance to kind of celebrate this. It's not just a couple people who are, always being heard about this, which I think is great. So what happened was from in the last 6 months was it started with the launch of the telescope in December on Christmas of last year, which was a really exciting and exhilarating time for me, but also one of the most nerve-wracking days of my life. I don't know if you've all had a chance to ever have a moment where the entirety of your career is sitting on the top of a rocket that you're watching on a live stream, but it's kind of a terrifying thing. And Christmas morning, I had that opportunity, and luckily the telescope launched and went up into space and unfolded properly over the course of a month. And I'm not even going to talk about all that nerve-wracking stuff here because I want to get to the images. But after we got all the telescope unfolded and we turned the instruments on and found they worked, we went through a process of focusing it. And one of the early images that was sent down, I'm really glad that NASA decided to share some of our internal calibration images, was this specific alignment image, which shows a bright star we were using to make sure the telescope was focused. And I'm showing this because you're going to be seeing a lot of images today, and this is kind of this will be a guidepost for what we're going to look at. A lot of people look at this and their first question off the bat probably is, why does this thing have a bunch of spikes on it? And I want to explain this, that when light passes over surfaces, and there's physics professors hopefully in the chat here or watching who know this, it'll diffract, it'll kind of bend around the edges of stuff. And when light moves off of a circular mirror, it makes a very specific pattern of diffraction. But for Hubble had, and you'll see this in the stars, Hubble had these arms that held up another mirror. When a telescope light goes off of a primary mirror, the big mirror, off of a secondary mirror, and then back into the instruments. And that secondary mirror was supported by 4 arms. And when the light passed by that, it would make these spikes. You're seeing the act of light going not on a circular mirror, but on a mirror that is what we call a tricontagon, which is this really 30-sided polygon made of 18 hexagonal segments. But also notice that the JWST has these 3 arms holding up the secondary mirror, which is sitting out front of the telescope. All this works together to make this crazy 8-pointed star snowflake. I call it the nightmare snowflake. And it's what we call the point spread function. Anything that's in these images that's a point, meaning like a star or something that the telescope can't resolve as an actual blobby, will come out and the light will spread in a characteristic pattern called the PSF. And so you'll see a lot of these PSFs. In fact, there's another one a couple other ones right below the star. If you look just below the star, you can see a couple other PSFs from stars. But that just all has to do with how light is spreading off that. And I can post in the chat afterwards or during the question and answer session a big NASA explainer image that you could share with students and you can look at yourself that explains how this works. It's a really cool process. The other thing I want to show about this image is not just that it's really in focus, but that behind the star, there's a lot of other little dots that aren't spiky dots. They're not little point spread functions. Dots like, this one over here. And these are galaxies. So we live in a galaxy called the Milky Way. We actually live around a sun in one little corner, one backwater spiral arm of the Milky Way. Not in the center, but over near the edge. The Milky Way galaxy is 100 billion stars. And there are nearby galaxies around us. If you think about galaxies are like, if you were looking down from the air over Kansas, farmhouses are, and the distances between farmhouses, that's kind of how galaxies are in space, meaning that they're pretty big for how close they, they're not like if you took our sun and shrunk it down to a grapefruit, the nearest sun to where I am in Tucson would be somewhere in Peru. So the universe, the stars are really far apart from each other based on their size, but galaxies are all over the place. And as a result, when you look out into the universe, when you see stars, you're seeing stars in our own galaxy, stars fairly nearby. And when you look at galaxies, you're seeing outside of the Milky Way to really, vast distances. And I'm just showing you this image before we get to the full color images to show you that anywhere you point the telescope, even at just some bright star for focusing, you're going to get a lot of galaxies. I'm a galaxy astronomer. This gets me really excited. So this image came down, and it was a really cool thing to showcase, and people took this image and showed it with respect to other images taken of the same field by other telescopes to show the increase in resolution. It was very exciting. And we focused the telescope on all of the instruments. This is the initial focused sharpness check for all the instruments. And I'm showing this to show you that while I work on NIRCam is just one of the many instruments on board JWST. There are 4 main cameras and then this fine guidance sensor, which helps us point and align the telescope in places in the sky. NIRCam is the one in the very center. NIRCam is the primary imager. It's the one that took most of the pictures you saw this week. And it consists of 2 modules that are identical, that are side by side in the sky, and allows you to take, big, wide, rectangular images, essentially, or 2 kind of square images, and there's going to be an image I show you later that's just 1 square because they just neglected to show you the other square, which is exciting for us astronomers because it means there's extra data out there. So NIRCam is a primary imager, and it works, as you can see, all these NI, NIRSpec, NIRCam, NIRIS, it works at a wavelength that's different than the wavelength we see with our eyes. We see optical light. Red, orange, yellow, green, blue, indigo, violet, optical light. It's light where the sun gives off most of its light, which is why our eyes work to that. We're very sensitive to what the sun gives mostly. But if you go a little bit longer than red light to wavelengths that are at longer wavelengths, we go to something called infrared, which is a wavelength that's just beyond red, and it's at longer wavelengths for the near infrared, and then in the mid infrared it's even longer than that. And so most of the instruments on JWST were designed to look at near infrared light, slightly longer than we see with our eyes, and mid infrared. You can tell which one is the mid infrared instrument because we call it MIRI, mid infrared. It's the one up in the top right corner. And that's a really exciting instrument. It's a much smaller footprint on the sky, we call the field of view, than the other instruments, but it is one that allows us to see something the other ones cannot, which is longer wavelength light. And we'll talk a lot about that as we go on. NIRIS on the bottom right and NIRSpec on the top left are very interesting instruments in that they are designed to do something called spectroscopy, which is where they've got very fancy kind of prisms, effectively, that spread the light by its wavelength. So instead of just looking at a picture of a galaxy or a picture of a star, they can spread its light by its wavelength to look at the chemical signatures at individual wavelengths. And we'll talk about that with an extrasolar planet spectrum a little bit later and a galaxy spectrum a little bit later. But effectively, all of these things are going to work together on the telescope to really give us insights into understanding the telescope. I should say, I'm kind of talking fast. I'm pretty excited. I'm running a lot of adrenaline. There'll be a question and answer session at the end, and I'll also post a link to a video, or maybe Danelle can do this. This video that I made about JWST, which is geared towards people who have never heard of the telescope. It was made before the telescope launched, and I was really excited to get it out there. And it's a great thing to show your students if they're excited about wondering why we build telescopes like this. And it goes into a little more detail on infrared light and what that lets us see. It was developed with some friends of mine who do a bunch of really amazing graphics for Nickelodeon and Disney Channel and stuff. So it's incredibly awesome. Highlighting MIRI being a longer wavelength instrument allows us to, see dust that NIRCam can't see because the dust goes right by, like a light goes right through dust. Near infrared light passes right by dust. But mid-infrared light can be focused to look just at the dust directly. And so I'm showing on the right a MIRI test image, like one of the calibration images, compared with a similar wavelength image from a telescope called Spitzer. So a lot of people know about Hubble, but between Hubble and JWST, we've had many, many space telescopes and some that have operated at the same wavelengths that JWST has. So instead of thinking about JWST as like an older sibling of Hubble, you should really think about it as an older sibling of Spitzer. Spitzer's about 20 years old when it launched, and it opened the door to the infrared universe, but with a much smaller mirror. Maybe I think it was like 0.8 of a meter, 80 centimeters. And you can see what happens when you change the resolution there. Spitzer was an incredible workhorse for infrared astronomy and for astronomy in general, but it was retired a number of years ago. But just looking at the difference between the two should give you some insight into why we build big telescopes like this. So the last thing that was released just as a teaser before the images this week was last week or the week before. They released an image, not this one, this is a ground-based image from a 2.4 meter telescope that covered the whole sky. And I'm bringing this up specifically to you educators because where it says Sloan Digital Sky Survey here, this is public data that is of a giant chunk of the sky that you can use for a lot of very cool science projects. I have a physics professor friend in Chicago, and I've pointed him to a lot of projects that are Sloan projects, which are great for undergraduate students. So this is a fantastic resource where you could look at huge chunks of the sky, but it's at this resolution. And they released a NIRISS image. So NIRISS can take images as well, like NIRCam can. They released a NIRISS image showing how you what you get when you go to JWST, and you could just going between these two. I'm going to bounce between these two. You can just see the difference in resolution between ground-based to now. It's very, very special what this telescope was, and all of this is leading up to the release of these images this week, which is there was a lot of teasers to just show that, man, there's something special with this telescope. So on Sunday morning, I woke up fairly early, and I was part of a media briefing of a small select group of people who were going to talk with the media over this week about these images, and they showed us. Now, the images that I'm about to show you, all the JWST images, they were not made by the instrument team. They were actually made by kind of a fairly secretive, smaller group within the place that runs JWST. They convened a smaller group without instrument team people because they were so busy with making sure the instruments worked, to kind of find targets that weren't already being planned for observations to other scientists over the next year. Find targets that would showcase the telescope in an incredible way, all the modes of the telescope. Maybe make some stuff that hopefully will get some people excited about the telescope. They've succeeded, by the way. And they took those data and analyzed those data and reduced those data and put those data together, and all the data now are raw data and people are actually playing with them. I have a Slack channel just a couple windows away that is just people just diving into some of the data. But they showed, a lot of us weren't able to see the images until either last week or, in my case, Sunday morning. And I was sitting here right here where I'm sitting right now, looking at this on a screen, just freaking out. And I'm hoping that when you saw them this week, you also had a similar experience. I'd seen a lot of the test images. I have a bunch of JWST data sitting here on my hard drive from NIRCam. That's all of our calibration stuff, but I had not seen it at this, these stacks and with this coloring and stuff. And I was very excited. We're going to go through all the stuff that was shown this week and go into detail. Again, hold your questions to the end. And if we don't get to your questions, you can, send them to me after the fact. But we're going to start with a Hubble image here. This is a Hubble image of a field called SMACS 0723. SMACS just stands for Southern Massive Cluster Survey, which is how this group of galaxies was initially detected. And this Hubble image is not a particularly deep image. There's much, much deeper Hubble images that we've taken over the lifetime of Hubble, including the very famous Hubble Ultra Deep Field. But they couldn't observe Hubble Ultra Deep Field for these images, A, because it's not the right time of year, but B, because there's a group that's already laid claim to observing that, and that's the group that I'm part of, and we'll be observing that later this year, and it'll be a very deep, much bigger than what we're going to see here. But I'm showing this Hubble image to show you that this is a field that was chosen because it's part of a larger survey, and really because it has some very cool thing going on in the very center. So if you look at the very center of the image, there's like kind of a reddish fuzzy galaxy. That galaxy is incredibly massive, very, very massive, much, 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 much more massive than our own galaxy, probably by a couple orders of magnitude. A lot of mass in it, a lot of stars, and also a lot of substance called dark matter, which you can't see in the image. Light just like passes by dark matter, but it acts gravitationally on light. And what it acts to do is it acts to actually bend light, to bend the light around the galaxy, meaning that light that was going to go off in some direction, instead it's bent towards JWST or towards Earth. And so Hubble is picking this up, and you can kind of see this in that on the left and the right of this image, there's like what look like little wisps that are like little arcs. And those are arced lensed galaxies. Like the galaxy in the very center is gravitationally acting like a magnifying lens. And you're seeing very far away galaxies magnified and stretched in a really crazy way. If you find yourself around a wine glass in the next couple of days, take your wine glass and maybe a candle or some little point, source, and like look through the base of the wine glass at that. You'll see that the wine glass base does a very similar thing. It bends things into these little arcs. I always say this, and I wonder if anyone actually does that. I was at a place once where it was like a dinner party, and I was doing a talk like this, and I like asked everyone to do it, and like one person did. I was like, everyone, I want you actually to do it. And they all went like, oh, it makes total sense. It does. So JWST observed this as well, and so we're going to kind of move this a little bit and tilt it in a certain way right here. And I'm going to show you this first image right now. We're going to kind of fade into it. But what I want you to do is, instead of just looking at the very center thing, try to pick a part of this image where there's not a lot of little dots, maybe up, in the top left, or, the bottom or below, beneath it. Try to find some region where there's not a lot of little dots, because that'll make this a little more impressive. We're going to zoom in, don't worry. And also, if you are watching this on like your phone or something, you should try and find a larger screen. I gave a talk last night, this exact talk, and it was projected, which was nice. But if you are able to watch it on like a TV screen or something, it'll make this whole thing a lot better. Like, I really don't watch this on a phone, So we're going to zoom. We're going to fade right now from the Hubble image that existed to a deep 12-hour JWST NIRCam image. And it's just spectacular. So what you're seeing here now is the exact same field, the exact same galaxies. This is one NIRCam module, meaning there's another entire NIRCam module they did not show because it wasn't targeted on this. They just wanted to focus on this one. Just one NIRCam module showing this lensed field, SMAX 0723, and you are just seeing all kinds of galaxies. There is so much to look at here. There's just so much. There's galaxies of different colors. This is, again, a near-infrared image, but for the galaxies here, they're at different distances from us, which means they're moving faster at different wavelengths, or faster away from us, and their light is shifted to different wavelengths. So this is, the colors aren't exactly indicative of what the color would be just because it's infrared light, but also because of how they're shifted and redshifted. But really, everything in this image that's not a spiky thing, there's quite a few stars in this image, but if it doesn't have spikes on it, it's a galaxy, everything. So let's zoom in. Here is actually, I was really excited, this image, when it came out on Monday, the president released it, which has never happened in my life before, where the president has been like, I want to show one of the images that you and your team has worked on. And it was the front page of the Wall Street Journal. I'm showing this because this article where it says A6, so it's the front page, Wall Street Journal, A6. If you were to go to A6, there's an interview with me, and I was like really excited. And I was like really thrilled to be a part of this until I was like, I should go get a Wall Street Journal. And I did not know how to go find a Wall Street Journal. Luckily, my mother-in-law found one in a 7-Eleven late at night. So I was really happy. So let's zoom in. Here's a zoom in of the central massive galaxy. And I'm showing this because there's quite a bit of features across this image that are really wild. There are stars from this massive galaxy extending like to the left and to the right. This is a big cigar-shaped elongated thing because this galaxy is acted to kind of gobble up other galaxies. They've fallen in on it and been ripped apart and shredded to make a big galaxy like this. Gravitationally, they've been pulled apart. Our galaxy is eating galaxies right now. It just hasn't gotten this far in the process of doing that. That's why it has also accumulated so much dark matter as well. But you're seeing arced lenses on either side of the central source, and you're seeing pairs of them. Like if you look in the top right corner, you can see what looks like a bolo, right? Like a blobby with like a thing attaching a blobby. And this is actually two images of the same galaxy far away behind the main big galaxy, bent by the gravity such that you see two images of them. And with this type of gravitational blob, you're going to expect these types of things. And if you want to look this up, this is Einstein ring, Einstein gravitational lensing. There's a lot of literature and great images on here to share with students. My favorite lens was imaged by Hubble called the cosmic horseshoe, and it's like almost a full Einstein lens of two images of a galaxy that's far away that I studied for my first paper. But you're also seeing that we can start to see little, if you look, there's, at those lenses, there's like little blobs along the tails between the two. There's these little, and I don't know exactly what those things are. This image has offered us so much to understand and look at and for scientists to chew on. It's a really complicated and interesting image. If we look at another region right here, you can see one of my favorite galaxies in this image, which is there's a pretty bright galaxy in the bottom left, and it looks like it's wearing a little hat or like a Salvador Dali melted clock on top. And what it's doing is there's a faraway galaxy on the other side of it that is gravitationally lensing just around it to make that crazy weird melty clock thing, or pizza dough thrown in the air kind of thing. And that's a distant galaxy that gravity has given us a chance to see it in magnified view, which is a really cool trick of how gravity works, and why this field was initially targeted was because of that. But also, again, I want to urge you, all the ones with the blue and red spikes, the diffraction spikes, they're stars. Everything else in this image is a galaxy, and there's galaxies in little smudges all over the place. If you were to change the contrast, you would just see galaxy upon galaxy all the way stretching back. So here's a Hubble image, and I'm going to kind of fade in the NIRCam image. I just chose this random chunk of the sky right here to be like, well, let's see what we can do. And so we'll go back and forth between this because it's really very spectacular. But as I just fade into the NIRCam image, you can just see how every part of this is filled with galaxies. Even better than the people who saw this last night, you can really see all these little fuzzy blobs that you see that are like in the black parts of the image. They're not noise. You'd have to really blow this up to see the noise. They are actual galaxies. But then on top of that, if we do that, look at this one on the far right that in the Hubble image just kind of looks like a weird spike. And as you fade in the NIRCam image, you can just really see that we're seeing a galaxy that has all kinds of star formation. You know, this is a view of the universe that Hubble could not give us because it's at infrared wavelengths that Hubble could not see. So for a lot of these galaxies, we're seeing the light that Hubble was not able to, which based on the redshift of the galaxy, all the light's been pushed out out of Hubble's wavelengths. We're seeing it as it might look from here, from the Earth, which is really incredible. This is one of my favorite things to go back and forth between. This one right in the very center is what I want you to focus on at first. We'll go back and forth. This is the Hubble image again. And the one at the very center, in the Hubble image, if you were a galaxy astronomer, you'd look at this Hubble image and you'd be like, man, I don't know what to make of that galaxy right there. Is it one galaxy? Is it a couple galaxies? What's actually going on? And it's very easy to see when we switch to the JWST image that it is one galaxy with knots of star formation, and then maybe another nearby neighbor galaxy as well. It's really incredible. You can see that this is a galaxy where spiral arms are forming. So let's bounce back and forth between those two. Also, notice the red star has the 4 diffraction spikes, which are from the arms of Hubble versus the 6, 8 little spikes on the JWST PSF there. I'm not monitoring the chat, so hopefully people are really, oh good, I'm just getting a lot of what I'm expecting, which is beautiful, exciting, wow, this is great. I'm bummed because when I gave the talk last night, we had people who could go ooh and ah. So if you want to ooh and ah to yourself, send it mentally and I'll hear it, which is really great. So I'll go back and forth one more time because now I want you to, again, while you do this, every time you do this, pick some new region of the sky to look at because it's really, this image just is giving and giving. And it's one NIRCam field of view on an instrument that has 2 of these fields of view. And we are going to be tiling the sky and tiling regions much, much larger than this to get images way deeper than just 12 hours to give us an insight into the universe. But with one image, we've already had there are people in that Slack channel who are just looking at individual objects right now. And I bet by the end of the week, there'll be papers on galaxies inside of here, probably on this galaxy. So on the top, I want to look at the top left. This is a Hubble image. And then the right is the JWST image. And you see the really red galaxy in the very center-ish, center below. That galaxy right there is a galaxy that, based on Hubble data that existed, it hinted that it might be pretty far away. The JWST data really nails it. And as a result, they took the NIRCam, or the NIRSpec instrument, and actually took a spectrum. They took it and focused on it to pass its light through a prism and look at it as a function of wavelength. And in the very bottom, you're seeing this. This is kind of a technical thing. I'm going to show one more spectrum in this, actually a couple more spectra, but I trust you. You're all educators. You're seeing on the bottom on the x-axis wavelength of light. For the near infrared, that's between about 0.9 microns, which is 900 angstroms, right near the edge of where human beings' vision cannot see, out to about 5 microns. And JWST NIRCam and NIRSpec, that's where they focus. So this spectrum is between 3.4 microns wavelength of light to 4.8 microns. And the y-axis is how bright it is when you pass it through. And you're seeing that there's kind of these and they've colored them, these little spikes on top of a little set of mountains along the bottom. But the spikes they are what we call emission lines. Now what happens when an electron moves in a specific orbital, it pops a little photon of light off into space at a specific wavelength. And you're seeing them at these specific wavelengths, which we can compare how we see them in space at 4 microns to where we would see them on the ground. We would see this line on the far right that says oxygen at 5007 nanometers, or 500 angstroms, and maybe I got that backwards, 5007 angstroms of 500 nanometers. My brain's a little frazzled right now. I do everything in microns, so that's why. And that 5007 is a green wavelength we see with our eyes, but the fact that we see it at 4.7 microns means that this galaxy's light has been shifted out into the near infrared. And we can do a pretty simple calculation by dividing those, two numbers, actually, like doing a division, and you end up getting a number called the redshift. And that redshift of this galaxy is about 8.5, which only doesn't mean, it means stuff for us astronomers, it means it's really far away, but for the layperson, it means that we're seeing this 13.1 billion years into the past. We're seeing this galaxy in a universe that was only some number of hundreds of millions of years old, which is really incredible. A lot of astronomers looked at that and they were pretty excited because this is one of the farthest spectra ever shown. But there were most astronomers who do that for a living were the most excited about something you probably didn't even pay attention to do, which is that right over in the almost in the center, there's a little thing that says hydrogen. To the next of it, there's a little spike that says oxygen. It's a pretty powerful spike. That line is called oxygen 34363. It comes from oxygen in the universe. And it's a tracer, when you compare it to some of the oxygen lines, it's a tracer of the metallicity of the galaxy, of the gas in the galaxy, meaning how much in this galaxy is the gas pristine left over from the Big Bang, or how much is it more complicated stuff? Our galaxy is very metal rich, and we know that because we're made of metals. I'm made of things that are heavier than hydrogen and helium, which is what the Big Bang made. The Big Bang just made hydrogen and helium, and then stars and galaxies with stars slowly built these atoms up, atom by atom, over time. And we can actually watch that because we can find lines like that. That line is the white whale for so many astronomers who for decades now have looked to see if we can see that line, not at galaxies at this distance, but much more nearby galaxies, because it's really very faint. And I have, friends who spent dozens and dozens of hours on the biggest telescopes from the ground here, hoping to tease these out in much closer galaxies. And then they just showed this on Tuesday as like, oh, by the way, here you go. It's marvelous. And this is just a hint of what we're going to be able to do with NIRSpec. NIRSpec is a very, very powerful instrument that the Europeans built, and I'm very excited about its capabilities just from this one spectrum they showed of a redshift 8.5 galaxy. And so, while a lot of this is going to be focused on imaging, I really want to highlight that the other capabilities of JWST are going to offer us a picture of what to expect, in the scientific future, and give us insight into how we came to be here. And so we'll talk about that a little bit at the end. Here's an image, the NIRCam image on the right, and then the MIRI, the longer wavelength image on the left. MIRI is not as sensitive. It doesn't have as big of a field of view as NIRCam, and it's not as sensitive, but it works at longer wavelengths, which is why it may at first glance look not as important or not as exciting. But the thing about MIRI is that because it's operating at longer wavelengths, it gives us an insight that we have literally never had at this resolution. We've never been able to see galaxies like this. And, the really red ones in MIRI tell you something about incredibly dust-obscured galaxies. There's dust everywhere in the universe, and it gets a lot in the way. And in galaxies, it'd be really hard to see through that. Hubble couldn't. And so Hubble would never be able to see a lot of these. And I think that as we get better instruments, there's a lot of these things, and now with MIRI, we're going to really find that the universe has a lot of dust, and we are, and things have been hiding behind that dust. And this gives us a kind of teaser about that. So this is a raw image. I'm showing you one of the raw images that I pulled off of the archive yesterday of the same field. So this shows you one of the raw NIRCam frames. A lot of these frames were co-added and stacked to make the final one. And you could tell that because when I show the next frame, it'll be larger because they moved a little bit. They dithered on the sky to stack them up so that all of the little bad pixels, and if you look close on your screen, you can see the cosmic rays, all that could be pulled out when we stacked it. And this is why we stack astronomy images, not just to get deeper. But these are the types of images I've looked at, which is why I was pretty excited after looking at so many images like this to see an image like this. It was pretty magnificent. So you can just see the difference between the raw image and then when you have a professional, like artist astronomer who can go through and really change the contrast, change the exposure, change the saturation, use different filters to tease out color when they can get an image that's just this beautiful. The next thing I want to talk about is a lot closer to home. I just showed you things that are some of the farthest we've been able to see with JWST. This is a lot closer to home. This is an artist rendition of a extrasolar planet that's like Saturn to Jupiter size called WASP 96b. It's been a subject of quite a bit of observation over the years. including people looking at its atmosphere. And the way you look at its atmosphere is that WASP 96b was selected because as it goes around its sun, it goes in front of the sun every once in a while, its sun, as it goes around. And so it blocks the light of the sun for a little bit, and on the other side, it blocks light of the sun on a regular period. And as it goes in front and blocks the light of its host star, you can actually see as the light passes through the atmosphere of the host star on its way to our eyes. And so what's really incredible is that that gives us some insight into the atmosphere of this planet. So this is a kind of very complicated thing. We're going to walk through this in a second, but this is a ground, like a spectrum that was taken of this planet's atmosphere before JWST. And look at how ratty the data's got, big error bars, it's all over the place. And they've tried to fit some models of what the atmosphere might be like to these data points, to this sodium feature, this thing that comes from the atmosphere having sodium in it. Sodium like in table salt, in a planet atmosphere much farther away. And what I want to focus on is the fact that there's like a kind of magenta line that does not fit very well. Doesn't go through the points, maybe some of their error bars a little bit, but it's not a good fit. The best fit, I think, is the red line, which goes through pretty well, goes through the data points pretty well. And this study concluded that because the magenta line doesn't go through, that indicates that this atmosphere isn't full of a lot of hazy clouds, which would mean it'd be very hard to probe into the atmosphere because the clouds would essentially make it very, very tough for light to pass through well. And the fact that this is a clear atmosphere, the red line does well, meant it was a really great target for looking at with JWST. So you notice that the wavelength on this x-axis stops at about 0.9 microns. Well, that's where we pick up with NIRCam. That's where we pick up with NIRISS. And here is a NIRISS spectrum showing a lot of wiggles of the same planet atmosphere. Wiggles that, because it's clear, allow us to see definitively that there's water in the atmosphere of this planet. So if you might think, well, maybe the Earth's only with water, we see water all over the place, and now we're seeing water in an atmosphere of an exoplanet. And there's other features that aren't even highlighted here, features that show methane in the atmosphere and a lot of stuff. And I was sitting next to my office mate, Thomas Beatty, and Thomas, this is what he does for a living. And he looked at this and said, I don't even think that this reduction is optimized, because he's been working on this as part of this science team. And the people who are working on this didn't have a huge amount of time to do this reduction and analysis. And I bet in the next couple of days, scientists will do a better job looking at this. And this will probably come out in the literature pretty soon. But this is just kind of the first pass that gets us very excited about how we're seeing water in an atmosphere of an exoplanet. We're going to do this for many, many exoplanets as we start to understand distant planets on the search for alien life. The next target was this Southern Ring Nebula, taken here as a ground-based image. The Southern Ring Nebula is what we call a planetary nebula. Back when these things were first discovered, astronomers saw these things with pretty low power telescopes and saw that they were colored in ways that were similar to how planets were colored. And they were also kind of blobby in the way that planets were, but they weren't exactly planets because they were fuzzy in the sky. They weren't like planets, are a little bit crisper than these objects were. You can see they have some fuzziness, and they didn't want to just call them fuzzy planets because that's not very professional. So they found a new way of saying that, and they called it Planetary Nebula, which literally just means fuzzy planet. And it wasn't until much later that astronomers were able to look at this with better understanding of what's going on, that they realized that what's actually happening in Planetary Nebula is it's not a planet at all. It's the end result of a star like our sun. Our sun is about, middle-aged right now. It's churning through hydrogen gas in its core and turning it into helium gas through fusion. That releases light that keeps us warm and lights up the room I'm in right now. Gives us the electricity that I use on the roof of my house, solar power. It's a great thing, and it all happens from this fusion going on in the core. But eventually, the sun will run out of hydrogen and it'll start going through helium and doing the same thing, and then it'll get to carbon, and then our sun will not be able to do much with the carbon. And at that point, it'll get very hot as the core compresses, and the outer layers will start to puff off of this entire star. The outer layers of the sun will puff off into space and leave the naked carbon oxygen core, a thing we call a white dwarf. Carbon will be arranged in a lattice like a crystal. So you can think of it like a giant Earth-sized diamond in space, even though it's a slightly different crystal lattice, surrounded by this beautiful gas. And when you look at this object with Hubble, you can actually see the layers of gas, from pushed off from the outer layers of the star. The bright object in the very center is actually not the white dwarf. It's a binary companion to the white dwarf. You can't see the white dwarf inside of this image. But this is the best that we're able to do with with Hubble, and the best we'd ever been able to do with any telescope until just a couple days ago, when we imaged the same object with both NIRCam and NIRIAN. So I'm going to show you the NIRCam image right here. And this is an absolutely gorgeous image. And we are seeing detail that Hubble could not see. This is rotated. So we're kind of rotating in like 270 degrees here to get this. But just look at how we can see how the white dwarf and this other star have like lit up this cavity of the Planetary Nebula, and you're just seeing all of the different layers of gas being lit up. These are hydrocarbons, so these are these are the hydrogen gas, essentially, it's molecular hydrogen coming off from the outer layers of the star being lit up. If we zoom in a little bit, you can just really see the detail in this image. And I'm going to show you at the end a website where you can go and download all these at the highest resolution right now. And I've already seen people who printed them out. You're totally free to do that. This is what's cool about things that are funded from American taxpayer dollars, is it's your images to do with and print out. I went down to a place here in Tucson to print them out, and I was like, oh yeah, just give me as big as you can of this one of these images. It's going to be great. And they would show me how much it was going to cost. It's like, all right, just give me as medium as you can of one of these images, because it's fairly pricey to print on high quality glossy paper. But I'd like to put all these up in our hallway to celebrate this. This image is just beautiful. So let's zoom in a little bit more at some of the detail. You can really see how the layers, and this delivers more and more as we look at it. All these layers of molecular hydrogen, which is formed on the surface of dust grains. So it'd be really cool if we could look at this with an instrument that showed us the dust, because the dust and the gas should live together. If the molecular hydrogen is forming on dust, they should live in the same region as the dust are. So wait a second. I really like this. And here is the mirror image, which shows the dust. This is directly showing the dust grains and where they live with respect. You can see that they look fairly similar. They've been colored differently because of how all of this has to be colored for our own eyes to see. But one of the cool things about this image is that you can see the white dwarf in this image. And it's at the very, very center of the image, there's kind of a red dot next to a kind of blue dot. That red dot is the warm in the mid-infrared white dwarf companion. And what's funny is that the way we knew this was a binary companion was because of someone, I think in the 1970s or 80s, who observed this object and wrote in a paper, there's a white dwarf binary companion in this, and it had 5 citations ever up till this week. And it's pretty incredible that many, many years later, we can confirm this result that was in a fairly uncited paper. And it goes to show that, astronomy, a lot of people weight things by how important they are, citing. But I really think it's important that we recognize that citations aren't a great metric, that sometimes great science is done by people in a way that they're not recognized in their time. And it's a bummer. But I absolutely love the Southern Ring Nebula image. I think it's just beautiful. There are images of the human eye where you like zoom in on the iris, and it reminds me of this. It reminds me of just how complicated the universe is. Here's another thing. In the background, so you can see up in the top the left of this image, and I'm zooming in a second, you can see what are background galaxies, and there's some over on the right. And these background galaxies, looking in, there's one on the top that's a edge-on spiral galaxy. You can kind of see the bulge of the galaxy, and then there's a face-on spiral galaxy in the bottom. Turns out the universe has galaxies everywhere, and the astronomers who worked on these, they kept calling them contaminants. They hated them. And what I think is contaminant, if you're a person who studies galaxies, is that there's a bunch of really cool galaxies in this image, and they've stuck a whole big nebula in the way. Get it out of the way so we can see all the cool galaxies. I'm just joking. It's very pretty. So the next set of images are really very special as a galaxy astronomer. This is the Stefan's Quintet, which actually Stefan's Quintet is right there. This is a ground-based image taken by Andre van der Hoeven. And it's a very famous set of galaxies. In fact, it's so famous that at the beginning of It's a Wonderful Life, the angels talk to each other about we got to help this guy, George Bailey. And the angels in the 1946 film, It's a Wonderful Life, this is an actual screen cap from the film. The angels are Stefan's Quintet. It's the galaxies that I just showed you right there as imaged in 1946 from the ground. And we'll come back to that in a second. This is the Hubble image of Stefan's Quintet. Just to give you an idea, there are 5 galaxies in this image. I'm going to label them all right here by their NGC number. 2 galaxies are right next to each other, so that's why it's at 7318A and 7318B. And NGC 7317, 7318A and 18B, and 7319 form a merging group of galaxies. Those 4 galaxies are actually in a merger, and that's why they have the crazy shapes they do, because gas in the galaxies, as they go whipping by and around each other, just get thrown out in the way that, like, you know, if you ever watch a destruction derby, you can just see that cars, as they crash into each other, throw parts of cars all over the place. You're seeing parts of cars in this crazy demolition derby of galaxies. 7320 looks like it's part of it, but it's kind of pretending. It's much, much closer to us than the other galaxies. And so it's just an interloper. It's a cool interloper that it's so close that you can see it in, you know, similar size like that. But it is, in fact, a much, much closer galaxy and has not gravitationally bound to the other galaxies. And so this gives us a cool opportunity when we look at this, because we can both see the cool interacting galaxies with NIRCam and MIRI, but also if a galaxy is close enough, we can start to see individual stars. So there's a lot that you're going to see in this next image. I'm going to show you a combination next of the NIRCam and MIRI images together. We're actually going to, and this is what it looks like, which is spectacular. I should have put these so that they do the same zoom thing, but there's a kind of rotation stuff. But like if I bounce back and forth, you can really see how much you see with NIRCam. Now, if you look at just the raw NIRCam image, it doesn't have some of the cool dust features and shock features in this, and we'll talk about that in a second. But so they've added these two together. But then also notice, before we go into looking at the galaxies separately, look at how many galaxies there are in the background. There's galaxies everywhere. Sorry, everyone who thought they were contaminants. Sorry, everyone who hates that there's galaxies all over the universe that get in the way of the stuff you care about. But galaxies are wonderful to understand, and getting so many of them is so exciting. This is the largest of the images when they tile them together. Like, this is the largest region on the sky. It's a very large region. They have to do a bunch of NIRCam tiles to get this image together, which meant that they had to take the images and move them around and stack them all, which is a very complicated process. So let's zoom in. On the left, you can see 7320. And as I said, look at the individual stars in another galaxy, which is important because there's astronomers who want to understand how stars are born in large groups in a galaxy. And by looking at individual stars, they can trace the life cycles of a galaxy's stars, you know, by virtue of where it is along the galaxy, which is very, very exciting. And on the right, you're seeing a zoom in on 7318A, B, and then 1719, where you're seeing this shock feature that looks like a crazy seahorse. And that's a shock feature because the galaxies are plowing into each other and getting and exciting all this gas. The gas is plowing into each other and getting excited energetically. And you're seeing this feature really amazingly. Here is the same image, but only the MIRI. And I show this because this is maybe my favorite image of the first ones that were sent, because this doesn't even look like galaxies anymore. This looks like modern art. It looks like psychedelia, to be honest. Not just because of the colors that they've given, but just because the galaxies don't look like galaxies anymore. You're seeing dust throughout the galaxies. It's really very, very spectacular. It's a beautiful image to look at, especially at the resolution we've got. I'm really very, very excited about what MIRI is going to tell us about the life cycles of galaxies, especially because if we look at the left image, it's the same galaxy, 7319. On the left and on the right, you're seeing, on the left, you're seeing the NIRCam and the MIRI. And in the center of both of them, you can see that there's kind of a spiky, you know, you're thinking, well, that's what Kevin said was stars, but that's actually not a star. Galaxies that have a lot of dust, especially galaxies with train wrecks like this and these mergers, they'll kick dust up and push dust out, and stars will make dust. And that dust means it's hard to see into the dust and see through to the centers of the galaxies and what's going on near the centers. Hubble had a hard time doing this. But with NIRCam and now with MIRI, we can just really peer through and understand the fact that inside of this galaxy, there's actually a supermassive black hole that's swallowing material. And you're actually seeing that black hole's light heating dust up in the MIRI image. You're seeing, that's why it looks like a bright, so from the very center, that there's an incredibly energetic process that's so powerful and bright that it's causing this brilliant point source of light like a star in the very center. This is a thing called an active galactic nucleus, and NIRCam and MIRI are going to work together to understand galaxies that host these things. This is what I do in galaxies nearby, which is very, very exciting. I'm excited about this image. Yesterday, I was giving out pictures of these at a planetarium, and this was one of the more popular ones, but the most popular one that was shown the entire time. I should just show this. This is just a really wonderful thing to see the optical through infrared to mid-infrared. And I show this because a lot of people think like, oh, we don't need to use Hubble anymore, but that's not true. Hubble is Hubble gives us a view on the universe that JWST cannot have and does not have because it's an infrared telescope. And we're going to use, you can just learn a whole bunch about a galaxy by looking at a different wavelengths. And we're in an era of multi-instrument, multi-wavelength astronomy where you really understand objects as a function of all their wavelengths, even out to radio and X-ray and ultraviolet. And we have incredible eyes in the universe through a very key range right now. And it's just, I can't wait to see what happens. So, I should also show you, here's that same shot from It's a Wonderful Life. And now let's show you, we'll tile the actual image on, which is great. And I think someone has already taken this image and redone the opening where they make it blinking like the way the angels do. But, this will be something as a fun Christmas card. If you've got friends in your family who are big It's a Wonderful Life fans, you can take and send this Christmas. The last image is of the Carina Nebula, but a specific part of the Carina Nebula. So this is the full Carina Nebula, and you're seeing a region that is many, many, many hundreds to probably thousands of light years across. It's a really, really huge region of space that is in the southern hemisphere and has quite a bit of gas in it that's forming baby stars. So throughout all the Carina Nebula, which is several thousand light years away, you're seeing baby stars being born inside of their cocoon of gas and dust. We're going to focus on the top right of this image, a thing called NGC 3324, which is a cluster of stars that have lit up a bubble. So let's zoom in here. This is a cluster of stars. This is taken with a 2.2 meter telescope. This is a ground-based telescope, 2.2 meter telescope, showing a bubble where the stars, when they're born from the gas cloud, they immediately have so much light, it just pushes the gas away and opens up these cavities, these bubble cavities, which is what you're seeing here. And we're going to look on the right wall of this. We're going to show you a Hubble image of just a tiny chunk of the wall. There's like a little thing, if you look, it kind of looks like a person's nose and mouth. We're going to kind of look at the nose region in a second with Hubble, okay? So in the image I'm about to show you from Hubble, at the top will be where the bright stars are just blowing away the gas, because they're so energetic. There's a lot of young stars that are really energetic. So here's the Hubble image showing this cavity, and these young stars. And it's a great image. Really big fan of this image. But let's move it up here and let's show you the near cam image with some MIRI. And then also, because for good measure, let's show you the whole image. And this is the JWST NearCam and MIRI image of the same region. And it is just something to behold. This is, I think, most people's favorite image. And I really, the colors and the detail in this, you could look at this for hours. And I'm absolutely floored when I saw this. So what you're seeing here is you're seeing about the energetic stars up in the top. Those energetic stars and ones that are off the image their light is so powerful, it's carving the cavity out, and you're actually seeing the process of the light pushing the gas and making it into these folds. Near cam is giving an image of a lot of the stars in this image, and not just stars that you're seeing at the top, but stars within the nebulosity in the center, because near cam can see through the dust. MIRI is giving you a picture of the dust itself, and that's where you're seeing all of the dust features around, like this blanket on top of the baby stars. And it's great for people who care about how stars are born, because with JWST and NearCam, we can peer into this nebulosity to see the baby stars being formed. So zoom in. Here's a region of dense dust that where, it's kind of holding on, even though it's being blasted by all this light from the baby stars, and it's still holding on. Because you should think about these regions not just as being like, it's having some more dense regions. Like, think of it like Rocky Road ice cream, where, there's some more dense regions and then there's some fluffier regions. And so in the dense regions here, you're getting a lot of dust that are kind of holding on. But even then, we can see stars within the dust. That's what you're seeing. If you look into that little thing that's poking out on the left, you can see some of the baby stars being born inside of there. I really like it. You're seeing the same process over on the right image, where there's kind of fingers holding on. One of the very famous Hubble images, the Pillars of Creation, imaged a region like this in the Eagle Nebula. I love the haze that was seen across, of the gas with all these stars, and it's just, there's so many stars in this image. It's really something special. MIRI also imaged this field directly, and you're seeing this where it really looks like fog rolling over mountains. I'm just, this is just directly imaging and looking at the dust. They've added some near cam here to get some stars in the background as well, and stars within the different regions. But like, there is just, this is again, remember, this isn't like the most exciting region and the most beautiful region. People will be imaging some of the very famous regions that Hubble has already looked at over the next year when they've already laid claim to those. This is just a region that had not already been chosen by, like scientists as a target to look at over the next year. And so you should be expecting to see images like this over the next year, all the time. So if you want to see the images yourself, as we come to near the end, nasa.gov/web first images, it really shows all. You can click on these, you can click and go find larger versions. You can find the 100 and something megabyte TIFF images, which you can go and take to your local printer. And, if you've got more money than I have, you can have them printed really large on glossy photo paper and mounted and stuff. They're just spectacular. But these images kind of made a splash. Actually, before I get into that, I want to highlight the fact that the first JWST paper was put out yesterday, and it is a characterization of the science performance from the commissioning process over the last 6 months. It's, these are the people who took part in that process. My name is right in the very center, like about 2/3 of the way down on the right. And I'm one of many. There's about 500 people on this paper, and that is a small number of the people who really worked to make sure this telescope has been able to get up into space and take the images you're seeing. But I'm showing you this because inside of that figure 1 had another secret near Canon image that was not shown. It's engineering grade, but it gives you a hint as the fact that there's going to be some more images hopefully in the next couple of weeks that are really exciting. This is an image of something you might be familiar with, Jupiter. This is a near cam image of Jupiter, and it's hard to look at Jupiter because Jupiter's really bright. You can see with your naked eye. The things you're showing tonight, you cannot see with your naked eye. This one you can. So they had to use a narrow filter, a really thin filter to throw away most of the light so that it wouldn't saturate near cam. And you're seeing some engineering grade images, but I bet you in the next couple of weeks, you're going to see some solar system targets in the way we've just seen the very pretty color images, and this is just giving you a secret, like little sneak peek. It's just kind of fun because this wasn't highlighted, but it was in that document as figure 1. And I've had this on my desktop for a couple of weeks now, and I'm happy that it's out that I can show other people. So it's made kind of a splash. This is Times Square the other day where they were showing the images on the billboards there, which is a wild. The New York Times front page for 2 days in a row was JWST images. And I mention that because for years I worked on this telescope, and I would tell people when the images come out, they're going to be front page New York Times style stuff, like above the fold. And everyone would be like, that's really, you aim for the stars, slugger. If you dream big, because they didn't understand the impact that this telescope would make. And they didn't really, they'd never heard of it. And they thought, fine, I bet it'll be exciting. And like, I am really proud. I have my copy of the New York Times in the other room that like it actually ended up happening. We have this beautiful image that can come out. It's really nice. If you get the New York Times, it's probably cool to see that on the front page. Google had a Google Doodle with JWST holding a camera that I assume must be near cam. It doesn't really look like that, but I think it's very charming. I thought it was a really cute thing. I've never done anything Google Doodle worthy, and now here we go. The Eiffel Tower lit up the other night at 11:30, sparkled on behalf of the fact that this is a world telescope, and the Europeans did a bunch of work on this, and so it's a celebration of their work, and I'm very excited about that as a person who's been working closely with Europeans for the last many years on helping with this telescope. And here's the president and the vice president talking with the head of NASA and one of our one of our JWST scientists, when they announced the first images. Like this has been the thrill of my life. It's been really, really surreal. So I'm going to finish here and answer questions you all might have. And if we can't get to all your questions, because we're only given 10 minutes, you can find me on Twitter and follow me on Twitter. I've been posting all about these sorts of things. And on the top of my Twitter page, my linked thing is the JWST video that I'd love if you shared with your students and watched. And then also a link to my YouTube channel where I do live streams of stuff about astronomy and stuff. But like, I've slowly had to transition my Twitter as more and more people follow me for astronomy, from my dumb jokes to the astronomy stuff that I do. And I need to maybe make a second Twitter that's just all dumb jokes, because I still got a lot of dumb jokes. But I'd love to answer questions about these images and about JWST and about this sort of thing. And I appreciate your time. Thank you. Let me look at the chat again.
Hello, and I'm going to help facilitate the stuff. I'm utterly and completely fangirling right now. You have no idea. I'm definitely super enthusiastic, and thank you so much in this crazy busy week that you could join us.
yeah, it's great. I'm at some point, like, I'm gonna reshare this so that if people have questions, I go back to the actual images. But I'm excited to do this, and next week, while it shouldn't be a vacation time for me because we have all these JWST data, my wife and I are about to go to to England for a week and then Ireland for a week, and it'll be a nice 4 years late honeymoon. But I will probably keep my computer near me or nearby to do a little data analysis on the side because it's such an exciting time. But I do get a break pretty soon. And I'm happy to do this talk because last night when I gave my talk at Flandre, I just pitched a softball game, and so I was like, it was a lot of adrenaline. So let's get some questions.
All right, so some of the questions that have popped up. So what's one of the top burning questions you want to try and answer in the near future? Kind of where are you going next?
So I'm an extragalactic scientist, and I work on looking at extragalactic astronomy, meaning I study really far away galaxies. And so we're going to get a lot of fields like this. There's already another field called Sears that is much larger than this, that the data came out today for like half of the data for that field. And that is going to be, you're going to probably see Sears images pretty soon as well, as people make pretty ones of those. But what's going to be really cool is in the next couple months, we'll have answers to some burning questions about galaxy evolution. So galaxies, and this I hinted at this when I showed the spectra. One of the cool things about why we study galaxies is that, as I mentioned, the universe started and it was a big bang, and there was light, and the light became hydrogen, a little bit of helium, and then for a long time that was what the universe was made out of, just hydrogen, helium, maybe a little lithium, a little beryllium. But like the periodic table at that point was really easy. It was 4 boxes, boom, easy. Wow, chemistry students would love it. But then something happened, which is that stars and galaxies were formed. And then what those stars and galaxies did was they lit up the regions they were in and like let light pass through, and the stars and galaxies started to build heavier elements, such that now we're made of the elements that were at some point made in stars. We could see this process. You saw this process in multiple images tonight. You saw the light pushing gas clouds together to probably trigger more star formation. You saw at the ends of lifetimes of stars how those stars push the gas and dust off into space, which is important because your molecules were formed in stars and on dust grains. When I show pictures of, like this nebula here, in the edges of this, you and your material that you're part of was in a nebula probably like this at some point, right? In a nebula like this, and in like the nebula like I showed of the Korea Nebula. And so what's cool about a field like this is that we can go and look at galaxies as a function of time, from the earliest galaxies to now, and watch as they slowly built up heavier and heavier elements. And in the next couple of weeks, as we get these data, and when we eventually get our JADES data later this year and on to the future, people will be able to just go and say, here is the history of how human beings and how materials that built human beings and built the Earth, how it came to be in galaxies, and we just watch that. And that's a burning question. That's very exciting. Next question. Good question.
Awesome. So cool. So what's in the dust? Have they studied the composition, or is that one of the goals? What is the
so
dust?
we have, so dust you should think of as like soot instead of like the dust bunnies under your bed or something like that. If you were to measure the dust in my house, it would be like predominantly cat hair, but that's not what it is in space. And the dust is primarily polycyclic aromatic hydrocarbons, which are, if you're a chemistry teacher, if you know a little about chemistry, carbon really likes to make these very specific rings and link up with hydrogen, and so there's these rings of carbon, these things called PAHs, that I'm having to Google this just to double check because my brain is a little bit, so a lot of carbon and hydrogen making these rings together. And on the Earth, those things are very much like what soot is, right? And so the composition is primarily carbon, but there's also silicates, and these dust grains are complicated, very small to some slightly larger. And there's a lot of questions about the exact thing, which is how do they get larger? Because we know that there's dust in our own solar system, and the dust is left over from our own formation of our solar system. We've sent craft that have passed into the universe to grab a little bit of it and bring it back to understand that we couldn't see how in the lab you could imagine carbon just hanging out near each other, but like how do the big carbon rings form larger things with silicates to make these complicated dust grains? And then on top of those dust grains, you get other molecules that will land on them, and then like a mixing singles bar, they'll mix to make molecules, hanging out together. And that is a way in which molecules that we have here on Earth are formed, right? And so this is a thing that's an active area of research, especially here at the University of Arizona. We have some dust experts, and why MURI is so exciting, because we can really take images and understand those dust properties. Next question.
Awesome. So I recall while you were talking that you said some of the structures in some of the pictures are unknown. So what does that mean?
Yeah, exactly. Like this is like, this right here, I wonder what some of these are. And it's because we've never had this view at this resolution. And this is why we build a telescope, not just to be like, well, we know everything and it's great, but just like, what could be that? And it'll probably be something fairly straightforward. And, this is lensed star forming activity or lensed globular clusters. And maybe it's only unknown because I don't know it right now, or because the astronomers haven't had a chance to look at it. But once we can look at this as a function of wavelength and not just in one JPEG that was released online on Tuesday morning, we can really get to understand this and look at it as a function of wavelength and get a better handle. But like, I think that one of the exciting things about fields like this and about data like this and about JWST is that instead of it being like, well, I wrote my paper and I'm really focusing on this one thing, there's a treasure trove of data, and people will be looking at this for years to come, and that's very, very exciting. And so these things of unknown structures and stuff, we will hopefully have understandings of them, and maybe you'll have to have me come out in the future, and we can talk about what we learned in the first year of JWST. What were our discoveries, or what's the new mysteries and stuff? It's exciting.
Awesome. Thank you. Thank you. So methane, does that indicate life possibly on planet?
This is a big question that people have about, and the thing is that we actually think that methane has ways in which it can be more naturally occurring. And so while it's often used as a biosignature, and this is not my field, biosignatures, there's entire conferences where people argue about whether or not something is a signature of life or not. It's most likely not a signature of life if it were found inside of a planet like WASP 96b. Why am I not remembering this? My brain is really having a hard time. But like, because it's a Saturn or Jupiter, unless there's some sort of weird alien Saturn floating cow that's farting. It is on our planet, it is in fact a pretty good signature of life because of the way that a lot of methane comes. But there are ways in which methane can be brought from comets and other extra planetary mechanisms. So this is the big thing, finding biosignatures. What's exactly a biosignature? JWST is going to give us a lot of help in looking at these things to try to understand why it might be, where this might come from. But good question. These are great questions. These are pretty complicated. I'm into it.
All right, well, I'll keep going with the complicated. So does the JWST data show any info for technetium or neptunium through spectroscopy, as those potentially being possibly naturally occurring?
The only spectra that we have seen right now, I have shown you. And so there are people who are probably analyzing the spectra. So that's like kind of, you have to wait. Ideally, it'd be great to see these, especially because to find some naturally occurring elements that are more rare, you have to look for very faint emission or absorption features. But I guarantee you within the first year, there's going to be people who are going to be looking at these sorts of things. I have not seen it. You're seeing this. And then the spectrum from a couple slides ago of like what some of the bright lines here, but this is a redshift 8. So for more close by things, but we also sometimes don't need JWST for looking at things like that. We need a spectroscopy that's at a higher resolution. I think JWST has that, but you're going to have to wait. Sorry. We have not, we're a little early on that.
So I don't know if you'll be able to answer this. What are the 2 oxygen isotopes that were shown in that lovely spectrum?
Yeah, so this one on the right is oxygen 3, triply ionized oxygen, and then the oxygen 3, 4363. So for oxygen 3, 5007 and 4959 are on the right, the 2 lines on the right. And they are just quantum mechanical pairs for like, triply ionized oxygen, and oxygen 34363 is another one. I actually don't know off the top of my head. I'd have to like do the math, and I don't want to do this right now for which oxygen line this is. I think this might be oxygen 1, so singly ionized oxygen. Oxygen 3, I like to say, when it was first discovered in astronomy, was really confusing because it was this green light that was inside of nebulae, and they were like, what is making this? And they had never seen it in the lab. And they called it nebulium, like an element only seen in nebula. And it turns out that it was triply ionized oxygen. And the reason it was never seen in the lab is that anytime we were in a lab, no matter how much of a vacuum we could do, we could never get oxygen into this ionization state. If oxygen were smacked by any collisions or anything, it would go out of the ionization state. So it has to be very rarefied, which you can only get in space. So it's incredibly rarefied, triply ionized oxygen, oxygen 3.
Awesome. Thank you for that. So what is one, now after the getting of the launch and everything like that, what are some recent struggles that have really stuck with you that you and your team have to work through?
Yeah, so there's been a lot of struggles, but they haven't been super severe in that commissioning an instrument in space is complicated. And, when you take pictures in space, it's different than when you take them in the lab. When you took them in, like in terms of something called stray light. You can read about this in the characterization document, this big, long document showing all the struggles and stuff. Like because JWST doesn't have like a tube around it like many telescopes, you get stray light issues, meaning light from outside of the field of view. That light will kind of bounce inside of the instrument. Even if we put baffles and stuff, you'll get a little bit, which will cause hazes across it. And that was a complicated thing, trying to figure out why we see these these features. And we had to do some simulations of the optical pathways to understand them and figure out how we can remove them through data analysis techniques, which is really great. Also, I was working on the team that looked at dithering, which is where, if the telescope moves little tiny bits so that we can co-add images, we need to make sure confirm that when the telescope's commanded to move these little tiny patterns, that it actually moves in those patterns. So I did a lot of analysis on that, and I would find that the commanded pattern and the recovered were different by a certain amount. It was really confusing until I talked to the team that was pointing the telescope and telling it to stay in the right part of the sky when we were taking images, because we need to hold the telescope steady. So we pointed a star. So if there's any drift, the telescope knows to stay pointed there. And it turns out that their instrument that was doing this would have pixels that were really bright because of defects in the way the pixel was made. And the instrument was thinking this is a star and using that. And that was an annoying challenge. But most everything's gone really well. The micrometeorite you may have heard of was, I think, really blown up in the media because everyone's really thirsty for JWST knowledge right now. But it impacted things very, very minimally. And we still not only have met our required threshold, but exceeded it amazingly. And the fact that one of the mirrors was struck by a micrometeorite only changed that by a tiny, tiny amount. So over the lifetime of the telescope, which we're hoping to be 20 to 25 years because of how good the launch was, we're probably going to see more micrometeorite impacts like that. And the thing is that's going to degrade the quality, but we'll take a lot of data before then. So don't worry.
Thank you for that detail. Kind of into the realm of structures of things, do all stars have solar systems related to them like ours?
So it's really hard to find the solar systems, especially ones like ours, because our planets are pretty close to our stars. Like the contrast ratio, if you wanted to take a picture of a planet, like the Earth or something like that around its star, it's as if I took one of those spotlights they use to advertise movies and pointed it at your eye. And on the very, very edge of it, I had a firefly, and you have to see the firefly. You couldn't, really hard. So we have techniques of doing this, and many of them are indirect for finding planets. And what we're mostly finding is that we think pretty much all stars have planetary systems. And the reason we don't see them is because it's really hard, not because they're not there. And so this is something that JWST, but also a lot of telescopes that have come online that are directly designed to look at these things, like TESS, the Transiting Earth Spectra Survey Satellite. These telescopes are going to give us insight to. But we think that most every star probably has planets around it, which is wild.
Awesome. When it comes to galaxies, since it's kind of your world, what's some of the weirdest, wildest, funkiest kinds of galaxies that are out there?
Oh man, there's lots. In the image that I just showed you, you can see, and I urge you just go grab this at the highest resolution because it's really wacky. Here we'll move a little on. Like in this one right here, I don't know if everyone can see, but there's in the very center, if you look just to the left of center, there's a weird, looks like an L, letter L. These are galaxies that are forming, and we're going to see galaxies forming, which means they're not going to be these beautiful spirals like the one in the top left corner. They're going to be irregular shaped and have clumps of star formation. And that's what JWST gives us. Also the fact that in the very center of this image is a galaxy like this crazy, enormous, long cigar shaped galaxy. Man, it must have just eaten a lot of galaxies to do this. And this is the question, what's going on there? How did it get so big and massive, right? This is, galaxies, and why we study them is that they are not just there's just one type of galaxy. There's a bajillion types of galaxies, and some of them have black holes in the centers, and some of those black holes are hidden by dust, and we got to find them. And how does the black hole impact the galaxy? These are what we're going to find. So, also with JWST, we're going to see how galaxies go from being weird, irregular, little clumpy things to the spirals we see today. We're going to trace the formations of spirals, and I'm really excited to see people making, charts where they put galaxies at various stages of spiral creation going out into the past to showcase this. So there's lots to learn. It's 12:03. I don't know how long we have. I don't want to go way over the time. But you know,
I got you. Don't worry.
Okay.
We gave you a little extra time because we're all like crazy interested.
Just-
So second to last question that we're going to do.
Okay.
What are you most excited about looking at with JW?
Yeah, I get this question all the time, and really, like, there's so many things. But to be really frank, to be really honest, is that this field is is really amazing as like a first teaser. It's a beautiful field of galaxies that just show the crazy complicated galaxies that exist. We have some pretty distant galaxies. I'm really into this picture, but this picture is of a field that doesn't have a lot of ancillary data, and the fact that there's only the only ancillary data really is the Hubble images that exist of it, and it's not that deep. So this field I've been kind of looking at over the last day when I've had time to, and it's kind of a bummer because you need that ancillary data to like really understand the multi-wavelength properties of these galaxies. JWST tells you something about them, but like having deep Hubble and stuff. So there are fields where Hubble has gone very deep. The famous Hubble ultra deep field that I've talked about, the most famous of the deep field, that was imaged by Hubble, and it's been gone over by almost every telescope has a bunch of data there. And in September, October, we have a program called Jwst where we've used 400 hours of guaranteed time that were given to us when we built the instrument, along with 400 hours of near spec time that they were given when they built the instrument, to look at the Hubble ultra deep field and a region around it that makes the Hubble ultra deep field look like chump change. It'll make this look like the tiniest thing. Like, at the resolution on my screen right now, our field will be maybe the size of my wall. It's going to be hundreds of thousands of galaxies. It's going to be far deeper than this, with ancillary data that's far deeper than what we have for this. It's going to really be the gold standard of deep fields. And it comes out, we have half of it, the data coming later this year, and then half of it coming next year because of how they split it. And it's going to be something that I guarantee you'll see a comparison where they go, here's the famous Hubble ultra deep field. And then they kind of like show you the JWST version, and then they zoom out and they zoom out and they zoom out and they zoom out. And they just show you how much data we have. And I'm really excited about that. That's called JADES. And it is the JWST Advanced Deep Extragalactic Survey, and I'm on the JADES team. I work on as part of the team on as the person who figures out how far away the galaxies are with some other folks that I work with, and that's a very complicated thing that I'm really excited about. So that's the answer to that question.
So cool. We will definitely be watching. So last question, and this was a mandatory one that needed to be asked. Doesn't all of this make you feel so small?
And the answer to that is no. I do not feel small. This is whoever asked this maybe was setting me up for the kind of take-home message of the whole talk of JWST in general and of astronomy and of why we do science at all. So I mentioned like the fact that, when we look at images like this or whatever, we're understanding things from the Big Bang to today. And, a lot of people tell me like, I feel so small and so insignificant, right? And yeah, we're small compared with the vastness of the universe. But when I mentioned that, like, this image of the Southern Ring Nebula, like, that's a place where atoms were. Like, the atoms that make you up, the energy that you're using to breathe, to listen, to be a part of this symposium, that was not created when you were born. You're borrowing that energy. You're borrowing those atoms right now. They're a part of you right now. And they have a lineage that stretches back inside of stars, past that, all the way back to the Big Bang when there was light and you were there. You didn't look like what you did. You were stretched out across the universe. And slowly over time, the universe puts you together atom by atom. JWST gives us an opportunity to watch all of the processes, to look at your past as atoms put together and energy put together. It allows us to look at galaxies like this, to watch as complexity in the universe put you together in terms of like, I need to have carbon somewhere in the middle of stars and belching out of stars. And then we can see in our own galaxy the processes going on now that happened in the past for you to be here. So I don't look at pictures like this and feel insignificant. I look at these and I see home. I see a part of who I am. It makes me feel very special. It makes me feel very honored that the universe, just given light and 13 billion years of time, put me together. And that, I never feel small because of astronomy. I feel, if anything, a burden and an excitement to go out and do things and create and give and love, because what has happened is the universe has put us all together individually, and then we've developed a diversity that has only made us stronger. And so when I think about astronomy and think about JWST pictures, I don't go like lie in bed at night and go like, oh, the universe, it makes me feel so insignificant. I think, wow, what an opportunity to do something with this weird life I've been giving, this weird spark of creativity and interesting, like interest in the universe. How can I go and give back, and how can I share, and how can I, and this is why I do talks like this, because if I've inspired you at all, if I've made you excited about it all, I've done my job. And I want you to turn around and give that back to the people you work with, because if we can continue sharing excitement, we can continue sharing the importance of human diversity and human biodiversity and human, and the ways we can work together to do good things. This telescope is a telescope that was built by people around the world. It is not an American telescope. It is a world telescope. It is a telescope that showcases how human ingenuity and human hard work can work together. So I just wanted to finish there, and thank you so much for your time.
Wow, Dr. Hainlein, that was amazing, and thank you for the charge. And we will definitely take that serious as we go out and make a difference as we start this next school year. We also wanted to honor you by making helping you make a little difference in this Umpqua National Forest in Oregon.
Right.
They experienced a wildfire in 2020 that burned quite a bit of the Umpqua National Forest, and the Arbor Day Foundation is working on planting saplings to reforest. And this is a beautiful picture from there, where you can see some of the new growth.
That's great. I love it.
And we would like to plant 25 trees in your honor.
Great. I have to go out and see him at some point.